All right, we're officially live right now.
Okay, so welcome back to the PQI 2020 summer session. Michael Hattridge is going to be the session chair of this session. And so I'll just hand it over to him right away.
Okay, so we have 3 talks today. Looking at the timing, it looks like all the questions are going to be at the end since there's no gap in between them. So just to get us moving, our first speaker today is Sridhar Tayur, and he is the Ford Distinguished Research Professor and University Professor of Operations Management at Carnegie Mellon University's Tepper School of Business. He received his PhD in Operations Research and Industrial Engineering from Cornell, and his undergraduate degree in mechanical engineering at IIT Madras. He's an Informs Fellow, a Distinguished Fellow of MSOM Society, and has been elected to the National Academy of Engineering. And his talk today is going to be about quantum integer programming. QuIP, take it away.
Thank you. And now I have to learn to do screen sharing. So where do I do that again?
Right down at the bottom, the green button.
Should be a green one.
Share screen, perfect.
And then anyone on the call, feel free to interrupt, pipe up if you have a question.
Yes, we want this to be a very interactive session, so feel free to stop and ask questions.
And you are going to give me a heads up with a minute or so to go, Jenny?
Yes.
Okay, how is this? Good?
We're not seeing the...
We cannot see your screen yet.
Yeah.
You're not? Okay. Share screen. How about now?
Not yet.
Not now either? Okay.
Not yet. No, sir.
You had it before.
Yeah.
So after click the share screen, you have to choose which window you want to share.
Yeah, I was going to choose this. Yeah.
Okay, we see it.
That works.
Perfect. Okay, double click it. All right. Okay, thank you very much for inviting me. Let me go through the agenda here, give you a few minutes of background and motivation, since you don't expect a business school professor to be on, on a session like this. I wanted to spend one slide on focusing today, since quantum computing is a very large area, and people come with preconceived notions of what they expect to hear. And my 25 years of MBA teaching has told me that setting expectations is more important than actually doing a good job. So I want to start with setting very low expectations so that you cannot be disappointed, okay? The main theme I want to show here is the fact that we want to solve some problems that come from supply chain and from engineering and production planning that we believe can benefit from thinking like a physicist. So think of this as an engineer who is thinking like a physicist. And I'll give you some early results, mostly computational, on what this kind of thinking has given us so far. And if time permits, we can talk about what does the future of quantum look like? All right, so feel free to, stop anytime, stop me anytime. So just to give you a background, previous to getting into quantum computing in 2017 summer, I was a founder and CEO of a software company called SmartOps. I ran it for 10 years. We built the software for enterprise inventory optimization, and I sold it to SAP. And more than 700 companies in about 60 countries around the world use my software on an ongoing basis. So if you read the newspaper on any given day, I would think that at least 5 or 10 of my customers are in the news, good or bad. Today's news had Bayer and Monsanto. Both of them were my customers. Medtronic is a customer, you name it. So if there's a name that you see in the newspaper that makes something physical, it's a multi-billion-dollar global company, it's probably running my software. Okay, so that's what I was doing for several years of my life. And then after I sold it, I started thinking there must be more to life than not doing anything. And so I thought, why not look into what next? I looked into quantum computing, and I said, what can quantum computing do for non-convex integer optimization? I'll explain a little bit of this because many of you are physicists. You probably don't know what some of these terms mean. And also the reverse question, can integer programming help in quantum computing? So this is something I started working on in 2017. Created the quantum computing group at the Tayur School of Business. You see David here, who is a PhD student in chemical engineering, who does a lot of work in nonlinear integer optimization. He also happens to have an, I think, undergrad and a master's in physics and things of that type. So he was an ideal candidate to kind of work with me on this. So the focus of today's talk, many times when you hear quantum computing, you normally think about the gate circuit model. So I wanted to tell you today that I'm not going to do a gate circuit model. So no noisy intermediate scale computing, no Hadamard gates, no swaps, none of that, okay? Second, when people think about integer programming, if you're in operations research, you think about branch and bound, you think of LP relaxation. In nonlinear stuff, you think about subgradient. I'm not going to talk about that either. I'm going to talk about a way of solving integer programs that uses something called test sets. I'm going to describe that in just a bit. Also, most famous results in academia, obviously, in quantum computing is in complexity, especially because of Peter Shor and of course the work of the search, unstructured search of Lou Grover. So you think about computational complexity. What's the worst case performance of an algorithm? I'm not going to talk about that either. I'm going to talk about the computational performance on some industrial size problems. And finally, again, when you think about quantum computing, you think about cryptography, thanks to Peter Shor again, or quantum chemistry and so on and so forth. Coming from a business school, as a production and operations management person, I'm going to talk instead about applications in supply chain and finance. So I wanted to set the stage today that if you came in thinking this is going to be gate circuit, no. Linear programming, branch and bound subgradient, no. Worst case complexity analysis, no. Quantum chemistry and cryptography, no. Okay, is none of that. It's something else. And part of my interest in this is to do something else in quantum computing. And again, coming from a business school, there is something called a blue ocean strategy and a red ocean strategy. Red ocean strategy means there are a lot of sharks, there's a lot of blood in the water, you don't want to go there. A blue ocean strategy means there are no sharks, there is no competition, you are the only person there. So I'm trying to create a blue ocean, for myself. Okay, just to give you some sense of how business school people think. So what is test sets? What are test sets and what is optimization? Essentially, you have an objective function f of x, which can be quite bad. Bad in the sense that it can be highly non-convex. It could be an oracle in this setup actually. It is something that takes x and says this is f of x. The big issue here is there are constraints. Ax equal to b. A and b are given. Later on, I'll take some structured matrices A, which are going to be 0, 1 of a particular type. But what is interesting here is x has to be integer. It can't have 1.75, 2.22, and so on and so forth. And binary, which is 0, 1, is a special case of it. But integer programming is hard. Binary programs are hard unless f of x is very simple or a is very simple. But generally speaking, bad f of x's appear in supply chain and in finance. X being integer appear quite naturally in business and engineering. And so trying to solve a problem of this structure is of great importance in engineering and business. So that's the background. Test sets have been around for a long period of time from a purely mathematical and intellectual perspective because they're beautiful and impractical at the same time. So you can imagine mathematicians love them because you can never do anything useful with them and they're very beautiful. Okay, I want to destroy that part, not by removing the beauty, but by actually making it practical. What a test set is, it says the following. Suppose you're at a feasible solution. You should take a step that improves that feasible solution using one of these directions. If you're unable to improve, using any of these directions, you're guaranteed that you're optimal. So a test set is a set of improving directions that say that if you cannot further improve, you are guaranteed of optimality. So it's a certificate of optimality, okay? So that's what it is, okay? So what you need for this to work is some way of getting a test set and some way of getting a feasible solution, okay? And that's all I'm going to do pretty much in this talk. A test set is called Graver basis. It turns out historically, when I look back, Graver in 1975 wrote this paper. I believe he was a CMU professor, although nobody can confirm it. It's not important exactly its definition, but I'm just giving you the background that these test sets exist. They are finite. They're extremely hard to compute classically, and therefore nobody in their right mind, other than Gerard Conisjols, who is my co-author, would try to write an algorithm for it classically. But again, he's a mathematician who doesn't expect to make money doing it. He just wanted to write a paper that says, I have an algorithm for it. I actually want to use this quantum computing in some form to say, can I get a partial Graver basis? And you will see the method that I'm proposing here. I don't want the full Graver basis. I just want to have a decent number of Graver basis elements so that if I have a decent number of feasible solutions, not one feasible solution, but a decent number of feasible solutions, then starting from every one of those feasible solutions, taking these Graver directions, I want to improve until I cannot improve any further, and then say, you know what, I think I found an answer way better than you can find otherwise. Okay, so it's a very simple heuristic, and it works for a wide range of objective functions because Graver basis is theoretically shown to be a test set for an incredible amount of objective functions, okay? So the overall picture of this talk is you're given an objective function that's very bad, an ax equal to b, an x integer. I'm going to use one call to a quantum computer to get something that gives me a partial Graver basis. I'm going to use a second call to get a bunch of feasible solutions. And from each of these feasible solutions, using this partial Graver basis, I'm going to walk until I cannot improve any more. And I'm going to report the solution and say, beat this. Okay, that's all the algorithm is. And the rest of the talk is showing you how good it is. All right. So we got access to D-Wave 2000 Q. I know some of you don't consider this to be a quantum computer, but for this talk, let's pretend it is. And this came through NASA, USRA, some kind of an RFP that was there, RFI. And we started playing with this. And so what we need to do is to represent the problem into D-Wave, let D-Wave run twice, once to give us a partial Graver and once to give us feasible solution. And then I walk from these feasible solutions until I do no better, okay? So that's all the algorithm is. You probably know adiabatic quantum computing way better than I can ever explain. But what is different from the gate circuit model is a different way of doing quantum computing called adiabatic quantum computing. And part of that is something called quantum annealing. And D-Wave is supposed to be a quantum annealer. So I'm just kind of telling you that it is a different kind of quantum computing. You have to embed the problem into this hardware. I won't go into it today, but I'm happy to talk to folks after. In fact, David and I wrote a paper on using integer programming to find good embeddings. So that's the example of integer programming helping quantum computing, although this talk today is how quantum computing is helping integer programming, okay? So I took a problem that is well known in finance, very bad objective function, capital budgeting, and has constraints. And I said, I'm going to do one call to get partial Graver basis. In this case, actually, I got most of the Graver basis. And then one call to get feasible solutions. I'm going to walk. I'm going to see how it does. And it turns out each time you call D-Wave, it gives you 10,000 solutions. 6,500 happen to be unique. So you have 6,500 feasible starts, and you get a bunch of Graver basis elements. And you walk, it takes about 24 steps before it can't go any further. You report the solution. You've done hundreds and hundreds of problems, and pretty much every time it has given the optimal solution. Each call to D-Wave is about 0.3 seconds. So this whole process is about 0.7 seconds. Okay. The problem is you can't represent bigger problems because D-Wave has only so many qubits. It has a certain connectivity requirement, which means you can't embed all the complexity that you want of the constraint. And most critically now, the coupling strengths between the qubits that they have very little fidelity. So different numbers, different distinct integers that you can represent is very limited. And therefore, until they increase the fidelity of the coupling, until they improve the connectivity between qubits, and until they increase the number of qubits to begin with, this is going to be more of a toy to play with and not really competitive with respect to like classical methods. So that's kind of the state of affairs. But so we started asking, what can I do today now that I've learned some physics? And could we look at specially structured problems, basically matrices A? It turns out quadratic assignment problem, quadratic semi-assignment problem are examples that are very commonly seen in our practical problems and have very good structure, that for these problems, I can find feasible solutions as well as graver bases using a recursive algorithm, completely classical. They're not polynomial time, but I can do it. And therefore, I don't need a quantum computer anymore. So for these problems, we did some tests with classically available commercial general purpose solver, which is Gurobi.
You got about a minute.
Want to show you two charts. And what you can see is red is our method, blue is Gurobi. Small problems, Gurobi is better than us. As problems become larger, Gurobi hangs, but our method keeps on going, whether it be quadratic assignment problem, quadratic semi-assignment problem, whether it be a different type of quadratic semi-assignment problem. Most importantly, this is the last chart I want to show computationally before closing out. The blue stars are the time Gurobi takes. The brown circles are the time we take. So what I really like about this, again, as a software CEO, is not only can I solve big problems faster, see the consistency of my time. You press a button, 1 second later, you get the answer, more or less. Okay, so that's what I wanted to highlight here, that we can actually solve important classes of problems now that I've learned a little bit of physics without using quantum computer at all. I think this is a vision that's out there, that there's going to be a quantum computer up in the cloud and we are supposed to use it. I actually think the hardware that is thinking is many, many, many years out. Fred probably knows more about that kind of physics and hardware. I have become fascinated with something called oscillation-based computing and coherent icing machine and things of that type. And in fact, created a prize for undergraduates at IIT Madras to create a prototype. So if time permits, we can talk about whether this is actually more feasible as a non-classical method of solving problems. Basically, I want something that creates multiple solutions of an icing formulation. My last slide. Why do I like being a professor? Because you get to do fun things that might actually change the future. Let me stop there.
Thank you.
I have a quick question.
Sure.
So do you think that the speed of human ingenuity will outpace the speed of hardware development? So we'll always be thinking of better classical ways to maybe, quantum-inspired algorithms, that will always
I think in the next 5 or 10 years, I see great improvements in new kinds of classical algorithms because we are learning new things from physics. Classical machines are getting better. So I think to beat classical is going to get harder and harder because I think there's a lot of lead and of course, if people know there's a race, they're going to spend time on it. Again, I don't know much about the super cooled qubits and things of that type. It just looks very complicated. The physics, the engineering, the number of qubits that you can hold, the kind of decoherence time, et cetera, it seems way too complicated. I mean, again, as I said, I'm looking at it just from a business school perspective. that it can actually be competitive in a commercial arena in the next 10 years. I don't see it. So I think of it as for the next 10 years, human ingenuity, faster and faster classical algorithms probably is the commercial way to go.
Quick question.
Sure.
When you did the comparison between the classical solver and the annealer, what was the hardware platform that you ran the classical solver on?
Yeah, regular laptop like this, MacBook Pro.
Because, you know, are those, I mean, there's a problem here in that I think those solvers aren't necessarily available on supercomputer class machines, but some say it's a super machine.
Yeah, we just did it on regular available laptops because I'm writing in C++, running it and running Ruby and things of that type. I think there are ways of making this much faster. I think that there are much faster. I think that's where you're going with this. Even within classical, you can use GPUs. A lot of parallelism that's built in here, and so I think a lot more can be done even within our algorithm to speed it up, let alone change the classical hardware architecture already available to make it fast. I think there is a lot of room already still available today for a good engineer really to do it.
No, and I think, of course, you know, we're not at a point where any quantum machine is going to beat a classical machine, a supercomputer. But I think that it's super exciting. I think that not only is it applicable to D-wave annealers, but also to these coherent icing machines, and also potentially, and also to our more conventional gate machines that have algorithms that do annealing. So I think it's all interesting.
Okay, thank you very much for the questions. I think to stay on time, we need to move to our second speaker. So Fred Chong is the Seymour Goodman Professor in the Department of Computer Science at the University of Chicago. He is a recipient of the NSF Career Award, the Intel Outstanding Researcher Award, and 8 Best Paper Awards. And I think it's going to be particularly relevant looking at his background today, that he is also the lead principal investigator on the EPIC project, which is an NSF expedition in computing, which sounds like you should be going somewhere, but I think you're going to tell us that's an intellectual expedition, not a physical one.
That's right. I think expeditions is NSF Computer Science's center, and they're meant to be high risk, high reward. Like an expedition to the Arctic or something like that.
Okay. Well, take it away, please.
Okay. Can you see my slides? Yes.
Yep.
Okay. Great. So I'm going to talk about gate-based computing. And I think it's actually quite complementary to the things that Sridhar talked about. And also, as was mentioned, this is an expedition in computing, which this coherent icing machines, that $10 million project is one of the newest ones of those. Ours is from the previous generation 2 years back. What is this? What am I going to talk about? I'm going to talk about how to make algorithms run much more effectively on physical hardware. And what we're going to do is we're going to actually close the gap between the algorithms we want to run and the machines that we expect to have in the next 5 to 10 years through what we call a co-design of the software. And I'll tell you what I mean.
Fred, sorry, just to pause you for a second. Could your audio, at least to me, is pretty broken up. Are other people hearing you kind of broken up? Could you maybe disable your video and see if that helps?
Yeah, it is quite broken up, yeah.
Sure.
Sorry to lose your face, but I'm having a little trouble following you.
Sure, let me, hold on.
Yeah, not that video. We want to see the slides. I mean, we also want to see it.
Yeah, I think I need to maybe stop share for a second. And then, here we go.
But I think I agree with Michael. It's probably good to try this.
Hopefully this will help.
Okay, shoot. Sorry to interrupt.
Sure. If you have any problems, let me know. I can switch to a different internet.
Okay.
Okay. So this work is the result of a large team that spans algorithms to hardware. We're lucky enough to have sort of some of the original algorithms people at MIT, Peter Shor and Ike Chuang and Aram Harrow. And then we have physicists, technologists, experimentalists at Princeton and Duke. And then we have computer scientists at UChicago. And then we have education at Santa Barbara. And so this is a sort of full stack effort. And I'll get to where we're going with this. But before I start, let me just give you, sort of the computer scientist, computer architect view of where we are, right? I think quantum computation, especially in this gate-based model that we're interested in, is really exciting to us because it is the only technology that we know that can fundamentally change what is computable, because it's the only technology that we have that if we add a device to our machine, it can potentially scale the computational power of that machine exponentially. And that would allow us to solve currently intractable problems, as was mentioned in chemistry, but also simulation and also optimization, which could lead to interesting societal benefits. Another interesting thing as a computer architect, as an industry, classically, we've been somewhat addicted to this notion of exponential scaling of our hardware, right? So we have Moore's law, which scales the density, but more importantly, something called Dennard scaling, which allows us to scale the computational effectiveness of machines without scaling the power consumption. Unfortunately, those things have ended, especially Dennard scaling, which you might notice that machines don't really get exponentially faster anymore, classical machines. They just get more cores in them, but they can't actually necessarily perform exponentially better. So quantum technology gives us a sort of specialized domain in which we can continue to have some amount of exponential scaling as we go forward, which we're, as I said, somewhat addicted to as an industry, but also for applications that require more and more computation. And also, as was mentioned in the last talk, studying quantum computation leads to more insights in classical computing. It's led to better algorithms in chemistry, physics, and cryptography classically. And there's this healthy competition between quantum algorithms and classical algorithms. Now, why now? Why are we so excited about quantum computation? This was also mentioned in the last talk. We're in what we're called the NISQ era, right? Noisy intermediate scale quantum machines, which John Preskill at Caltech coined this term. He also said this is a privileged time in the history of science and technology. And it really is. It's really exciting because for the first time, we have machines that we can't simulate classically. So in the very least, we're going to understand a lot more about quantum computation and how these machines work that we can't explore without having them. And optimistically, we'll actually be able to compute things using quantum algorithms that can't be computed with classical machines. Now, we already have machines in sort of the 53 qubit range. Unfortunately, 53 qubits, if you have 2 to the 53rd states in your machine, that's already quite a lot of computation, right? And that actually would already be better than classical computation, except that these qubits are noisy and the gates are noisy. So much of what we do in our project and much of what needs to be done in the next 5 to 10 years is how to deal with that noise, how to most effectively use these machines. Now, even though we're in this exciting time where machines have rapidly improved, we still have what we think of as a large gap between what we want to run and the machines that we'll have. Now, what I show here is 2 important dimensions of quantum machines. One is the number of physical qubits that you have on the x-axis, and the other is how reliable are the operations on those machines, right? So you need both these things to effectively run algorithms. And so on the lower left is where we started, where things were pretty bad. We're moving slowly to the upper right. I think you can see the 2019 square here that's closest to the upper right. That's the Google quantum supremacy experiment, that machine. But still, you can see that there's this pretty big gap between the algorithms we like to run and the machines that we have today and we may have in the next few years. What we're looking to do is close this gap. Now, how are we going to do that? We're going to use software to make these algorithms use many fewer qubits, many fewer gates, and be much more tolerant of error. In fact, we have this project goal, which is pretty ambitious, just to use the co-design of algorithm, software, and hardware to make things 100 to 1,000 times more efficient. Now, if you look at the history of how machines have improved, that's about 10 to 20 years of hardware progress. So we're trying to bring quantum computation, practical quantum computation, 10 to 20 years closer by designing software better and by feeding back to how machines should be designed. And the way we're going to do that is on the right, you can see this, what we think of as the software stack, or the stack of quantum computation. And we're actually going to take shortcuts through this stack and expose more physics to the software and to the algorithms. And I'll give you 3 examples today of how that's going to make things much more efficient. So this is it's actually one of our NSF slides of what did we do in the first year of our project. We have another one for the second year, but I'm just going to mostly use examples from this. And so we have these different thrusts in algorithms, programming environment, verification, and education. I'm going to focus mostly on this technology environment because that's what gives us these efficiency gains. And you can see that on the right, the outcomes are all sort of order of magnitude or better improvements. And our goal is to combine a whole bunch of these and get that sort of 2 to 3 orders of magnitude improvement. I'm going to talk about these 3 things. And I'm going to give you those 3 examples quickly in the time that we have today. And then I'm going to go and talk a little bit about verification and why that's important before I conclude. Okay, so let's look at these examples to get a sense of what do we do. Okay, so the first thing that we're going to talk about is what we call direct-to-pulse compilation. This is some work that I did with Dave Schuster, who's a physicist at CU Chicago. Okay, so here's a picture of our software flow. We start with a quantum program on the top, and then on the left side of this software flow is what we think of as the old way of doing this. This is the conventional way of doing compilation. We take a program, we compile it down to gates, something we called quantum assembly, QASM, which is essentially the theorist's view of what a universal set of gates is. But then we have to translate that set of gates to this instruction set architecture, the quantum instruction set architecture, which is essentially what the physical machine supports in terms of the operations and gates. So there's a little bit of a mismatch there. And then actually what we do from those low-level physical instructions, we go to microwave control pulses that actually implement the gates on a physical machine, such in this case, a superconducting machine. Now, we find that we can be much more efficient if instead we go down the right side of this picture, where instead we go to these quantum gates, but then we group them together into little groups, and then we directly take those groups and feed them into an optimizer and find a control pulse sequence that implements a big group of gates all at once. Turns out this will give us about 5 to 10x shorter pulse sequences. So what does that look like? So here on the upper left, I have a picture of a quantum circuit. If you're not familiar with quantum circuits, the things on the left here, the Qs, those are the qubits. So this is 3 qubits. These boxes are quantum 1 qubit gates. These things with the circles and pluses, that's what's called a controlled knot. It's a 2 qubit gate. So these are all operations that go from left to right in time. And then the outputs are on the right. This little circuit here is a part of something called quantum approximate optimization algorithm, which is actually a little bit like an annealing algorithm on a digital gate-based computer. We're going to look at, if you look at the bottom left here, we're going to look at just this little subpart of the circuit that's labeled G3. Okay, so this little shaded box in the middle. If we take that box and we take each one of those gates in the box and we compile them separately into pulses, we get on the upper right. If we take that box and we feed it into a gradient ascent optimizer and we directly try to find a pulse sequence that basically transforms the inputs to the outputs of the whole box, we get this thing in lower right. Okay, it's about 3x shorter and a lot simpler, right? So what we're essentially doing is we're treating parts of the circuit as a function or a transformation, and we're optimizing directly for that, taking sort of a shortcut through the compiler directly to pulses. And we find that exposing pulses to the software gives us much more efficiency. Now we can see this here. This is a whole bunch of different applications. On the x-axis, I actually show bigger and bigger groups in the circuit. Okay, so the ISA line, that's basically the old way. Going to the right, we get groups of 2, 3, 4, or even 10 qubits together, and we group them together and make one of those groups like that G3. Now, the bigger the group, the better the optimizer can do, right? Because it has more, it can take a bigger shortcut from start to finish. However, the bigger the group, the more serial it makes the computation. If your computation has a lot of parallelism in it, and you make a lot of big groups, you're basically taking what's called a dependency graph, and you're making it a group of big nodes, you're grouping things together, and it makes extra dependencies. So it makes things more serial. So what you see is on the left side, you have things, left column, I have applications that are more parallel. And so when we have bigger groups, it hurts them more. So the performance, is in the y-axis. So we start at 1, and going down is essentially normalized time. So going down is good, right? So you see it stops going down so fast because we start serializing. On the right column, we have applications that are inherently more serial, which means they're not hurt as much by this technique. And so you see that they keep getting better and better. So just to summarize, what we're doing is we're breaking a very traditional computer science abstraction, which is this notion of an assembly language. We're going directly to pulses. And we get about a 10x reduction in these pulse lengths and an average of about 6x. And we're looking to apply this right now experimentally to IBM and trapped ion machines. Okay, so given time, I'm going to move on to the next 2 examples. Okay, so here's an interesting example, which is we're going to compile to hardware, and we're going to be aware of the kind of noise and variation that the hardware has. Okay, so normally what we do is we compile a program for some sort of architecture like your Intel box, and then you can run that binary on any box. What we're going to do here is we're going to compile to a specific machine of a specific size on a specific day. Okay, why are we doing that? It turns out that if you look at the right here, this is some data on IBM machines, which are taken, it's taken day to day. So you can see on the x-axis, you can see the different days. And on the y-axis, on the top graph, this is essentially the quality of each quantum bit. Higher is better. You can see it very significantly every day. And you can see that some qubits are just really bad. This blue one is bad. Now, same thing for what's called gate error, which essentially if you do an operation between 2 qubits, these are different pairs of qubits on the lower right, you see it very significantly from day to day, and not even the same one is the worst on a particular day. So it turns out that it's very important to be aware of this data that IBM takes every day and adjust the way you compile to the machine based upon this data. So here's another simple circuit on the left. It's called Bernstein-Basrani. It basically guesses a secret string. And in the middle is what the IBM native compiler will do. It will take the computation and it'll map it to these little things that say P1, P0, P2, P3, and it will use these links that you see these little blue arrows on to accomplish the circuit. On the right is the optimized mapping. If you're aware of the fact that these red X's are bad pairs, like high error pairs in your machine, and these grayed out qubits are bad qubits, you try to avoid them. And you see that now it's mapped this computation to sort of the middle of the machine and avoided the red X's and the gray boxes. Okay, so what happens if you do this? It turns out you get about 28x improvement maximum and about a 3x average improvement in the reliability, success rate of your circuit. Okay, so here what I have is 3 different bars. The left bar is, the maroonish bar is the Qiskit, which is the native IBM compiler. And then the orange bar and the green bar are the new compiler here. And what it's doing is in the orange bar, it's basically only optimizing for less communication. And in the green bar, it's optimizing for both less communication and avoiding the bad qubits and the bad pairs. You can see that the green bar is the highest and significantly better than the maroon bar, which is the native compiler. Sometimes you don't even have a maroon bar because it actually just doesn't work on the machine if you use the native compiler. This has been very successful. It turns out that now IBM uses this compiler in their compiler. And in fact, it's also being integrated into Rigetti's compiler and IonQ's compiler. Okay, so the summary is about 3x average improvement. And it's better than the native compilers that we looked at. So it's actually been integrated into those machines.
Sorry, I have a question about that.
Sure.
I mean, you're saying that these qubits are varying from day to day. Like, how do you know that there isn't some change in the quality of the qubit in the middle of your computation? Like, it doesn't seem to me.
Oh yeah, that absolutely does happen, I'm sure. It's just that IBM only provides the data on a day-to-day granularity.
But then how can you reliably say that you have a better reliability?
Oh, well, we run it, right? So
you're saying that on the actual experiments, you're saying you get this.
On the actual experiment, we get better reliability. Yeah.
Okay.
We might get even better if we had hourly data, except that the calibration takes a lot of time. So there's some limit to how often they can calibrate the machine and give you that data. But yeah, I mean, it could be that every 8 hours would be better than every 24 hours. They actually calibrate twice a day, but they only publish the data once a day.
Okay, thanks.
Maybe I also had a quick question, if I may interrupt. So this sounds very similar to what we were doing in annealing, and usually there is this trade-off between how optimal, like how much are you willing to sacrifice in the embedding quality, or in this case in the scheduling quality, and how long does it take? Because this problem actually is NP hard. It's as hard as the actual problem that you want to solve in the quantum computer. So do you have any comments regarding that?
Well, I mean, the compiler actually uses an SMT solver. It uses the Z3 SMT solver. So it has a number of constraints and cost functions that try to balance those things, right? And it's trading those off. It actually scales fairly well because it's fairly constrained system.
Mm-hmm.
But I mean, it is optimizing for end fidelity, right? So
okay.
The embedding matters, the scheduling matters, everything matters.
All right.
Great. We can talk about that more next week. I think we're meeting next week.
Sure.
Right?
Yeah, we are. Thanks.
Okay. All right. So one more example. Okay. So now here we're going to expose something else of the physics to the software, and what we're going to expose is that instead of using 2-state qubits, we're going to use 3-state qubits, right? So ternary logic is actually nothing new. It's fairly, it's been a sort of a curiosity in classical computing, but has never really shown great advantage. Turns out that we're able to show great advantage, at least in a special case here for quantum circuits, and hopefully for less special cases in the future. So the interesting thing here is that in classical systems, we take a logic level, which is usually represented by charge or voltage, and we basically take that signal and we divide it up into 2 regimes, right, for 0 and 1. And then if we want ternary or 3-level bits, we would have to divide that same regime into 3 different pieces, and then it sort of makes the signal less and gives you problems with noise margins and things. So it's actually a more difficult proposition, it turns out, in the classical domain. In the quantum domain system, we have, in fact, many levels of a many-level system, and it just turns out that we only use the first 2 levels, right? And we ignore the levels above that. In this case, we're just going to use 1 more level. Now, there's an issue that there's more noise and more error in the higher level, so we will evaluate that. But here, I just wanted to point out that there's sort of an advantage that we have more levels to use, and so we can have Q-trits or Q-quarts or Q-quits. In this case, we're just going to look at Q-trits, okay? And then we have a sort of a new gate set. Instead of flipping a bit, we're now going to have this X plus 1 mod D or mod 3 in this case. And so we have a sort of a generalization of all the gates to Q-trits. Measuring Q-trits are hard, And so in fact, experimentalists hate this idea of using qubits if we're going to measure them, but we're actually only going to use the qubits in the middle of our circuits. We're going to have qubits in, qubits out. So we're never going to measure qubits. Okay, so we're only going to use what are called intermediate qubits. What are we going to use them for? Well, here is a very simple application. This is something called a controlled gate. It's a controlled Toffoli. So what it's doing is, if the top bits here, we have 5 bits. If the top 5 bits are 1, then do the thing on the bottom. In this case, it's a bit flip. Okay, so it's a multiple control bit flip. Normally, the way we do this is we have to build essentially binary operations that essentially compute the AND of all of these 5 qubits. Okay, and so we have to compute the AND. And the way that this works is we can do it very quickly if we have 5 qubits, if we have 5 extra qubits, which you think of scratch qubits or ancilla. And so then we can do that logarithmically, we can build a tree. So what we're really going to do here is we're going to build the same thing, but without those 5 extra qubits. Instead, we're going to take the 5 qubits we already have. Well, in this example, I think it's 11. And we're going to use the third state, borrow an extra state to sort of be the temporary qubit. Now, it's a little bit non-trivial. If we had Q quartz, like we had 4 states, then it would be exactly equivalent. We would just have an extra qubit sitting on our device by using the third and the fourth state. It turns out we can do this with the third state. And the way we do it is we build these little boxes that have these little 2s on them, which means that do this box if the qubits that say 2 are in the 2 state. Right? So it's just a generalization of this controlled thing. And it turns out we can build this logarithmic structure with qubits, and we don't need any extra devices. We just use the same devices with an extra state. Turns out this works really well. So the blue lines here, those are the old way. So on the x-axis is how big of a controlled operation you have to do. It is getting sort of ridiculously big going to the right, but shows the asymptotic behavior. But things like Grover's algorithm actually use really large controlled operations like this. On the y-axis, we have the circuit depth and the number of 2 qubit gates, right? So the circuit depth for the blue line scales really badly. It gets really big. The orange line is us. It's pretty good. In fact, it's asymptotically better, right? It's logarithmic instead of linear, assuming that you don't have a linear number of ancilla. If you have 1 ancilla, actually you can do a lot better. This is the gray one. But this is assuming that basically you don't want to use twice as many qubits as your circuit wants, right? Because our machines are small. So for the sort of foreseeable future when qubits are constrained, this is a really useful technique. On the right it's the gate count. We don't get an asymptotic advantage, but the constant is way better, right? Factor of, almost 2 orders of magnitude. Okay, but the important thing here is that we actually experience more error, right? So if we use the third state, more errors happen. So what we did here is we modeled how much error there is in our system, and we did it for the blue one is the qubit systems. The gray one is qubit with one ancilla. The orange one is qtrits. And then we ran it for SC, which is current IBM superconducting parameters, SC plus T1, which is current IBM machines with 10x better T1 time, so coherence time. SC plus gates is IBM plus gates that are 10x better, and SC plus T1 plus gates is both those things 10x better. So projecting into future technologies. In all those cases, you see that qtrits do much better. And that's because of the incredibly smaller circuit depth, where the operations are slightly more expensive. In fact, they cause more error, but there are many fewer of them, right? And so we actually do better. On trapped ions here on the right, the blue line is actually better, much better than the blue line for superconducting qubits, so the improvement is less, but it's still the case that these orange qtrit fidelities are better, right? And I think I maybe didn't explain that the y-axis here is how reliable is your result. So higher is better. Okay. Okay. Must be running low on time now. Let me.
I've still got like maybe 6 minutes or so.
Okay, good. Okay, so let me just summarize. It turns out that if we use these QTrits, we can have up to 70x fewer devices that we need. Basically, we don't need these NSA. We actually get better reliability because circuit depth is less. And we actually use a pretty conservative error model here. Error is probably not as bad as it looks like here. We don't actually use the third state much of the time in the machine. So then operations are less error prone than we're modeling. And we're now, this has generated quite a lot of interest with experimentalists and with hardware vendors. So we're actually running QTrit experiments now on IBM and Rigetti machines, and also some academic machines at Lawrence Berkeley. Okay. Let me wrap up with just one open problem that I didn't really have too much time to talk about. Now, I've talked a lot about optimizing by exposing physics, but basically exposing details to the software to make it more efficient. This is actually going to make another problem we have much worse, which is also a big research direction for us. And that is, how do we know that we've written a correct quantum program and that it's run correctly on our machine? So I have this picture, which is sort of illustrating this sort of ridiculous bootstrapping situation that we're in, sort of forklift on forklift, which is that, we've spent actually about 10 years writing software for quantum machines that mostly we can't test because it runs problems that are too big to actually run on quantum machines or simulate on classical simulations of quantum machines. And once we have the machines, we're basically pushing the boundaries of the technology so the machines are very error prone and noisy, right? So when we run our first quantum programs of any size on large quantum machines, basically there are going to be errors, and we need to know, are those errors from the software or are they from the hardware, right? And we have a technology for this, which is what we call in computer science formal verification, right? So there are formal methods to prove that your software is correct. Now, in classical computation, we basically don't do that because we think that's sort of hard. We'll just test it. We'll just run a few tests, and if it looks mostly correct, we'll be happy with that. But in sort of this quantum situation, we're really in this situation where we want to try to prove that things are correct. And we've just started to do some of this work, and some other groups have started to do this work where we're using different kinds of formal methods, theorem provers and model checkers to try to prove that our software is correct. This last bullet here called Certique is some work that we just did where we actually ran a model checker on IBM's Qiskit compiler. And we actually found, I think, 4 or 5 bugs in the compiler, because that's a compiler that's contributed by open source contributors. And it's very easy to have bugs that are sort of hidden in the compiler. Now, at a very sort of high level, there's this very interesting problem that what we'd like to do is we'd like to check useful properties of quantum programs in tractable time, hopefully polynomial time. But we'd like the quantum programs to still have what we call quantum supremacy, to have a quantum advantage over classical programs, right? So that means that we can only check properties that are not too close to actually being reducible to the answer, the solution of the program. Because if I'm able to check too well the correctness of a program and basically know what the answer to the program is, then I basically disproven that the program has quantum supremacy or is that interesting of a program, right? So we're in this sort of interesting middle regime where we're trying to find this middle ground. Okay, let me skip to towards the end. Now we are in this interesting time where, in fact, we already have a number of abstractions or layers in our software model across algorithms, programming languages, instruction sets, even physical control. IBM has this open pulse interface that we use. And this is great for experimentation and for modularity and reusing infrastructure. But I would argue, actually, it's too early to have, these layers. We need to break through these layers because we're leaving too much efficiency on the table, right? And we just can't afford to do that. So what we're really about here is trying to find where should we expose the details of the machine and the physics of the devices to the algorithms and the software. Now, I talked about this gap between algorithms and hardware. Now, there's this sort of interesting gap in time between what should we do in the short term for these small machines, and what will we do in the long term when we have many, many more qubits, more reliable gates. And the question is, how much abstraction can we regain? How much detail can we forget about as we go, to the right in this picture, right? How much of what we do right now is going to be useful into the future? Well, it turns out that, even classical computing is sort of backsliding a bit from the right to the left, because we now have transistors that are not so reliable, we have variability. And so, I think that it would be hard to imagine, I mean, who knows, 20 years from now, a future in which qubits are free and, gates are sort of infinitely reliable, such that we can ignore these problems of reliability and noise. And so I think that, in fact, many of the things that we learn today, where we're trying to optimize for these small noisy machines, I think will persist into the future as we move to the right. So let me just finish here with, I think quantum computing is at this very historic time. It's an extremely exciting time to be working in this area. Something that's really been missing is this, what I call the computer systems view, right? Looking like sort of bridging this stack from algorithms all the way to hardware, developing software that is aware of this connection. That can really accelerate the progress of technology and sort of practical use of these systems. And also, I think if you talk to companies and research organizations, the workforce that knows something about quantum computer systems is really missing. And in fact, we just released this book last week in an attempt to build the quantum computer systems workforce and research groups in this area, in which we try to describe this approach and some examples of this kind of research. It's part of what's called the synthesis lectures. So most universities subscribe to this, so you can download it for free. So if you're interested, I encourage you to look at that. And we have this, our EPIC website is actually quite extensive in terms of both our research and materials to learn about this kind of research, videos and tutorials and software packages, actually. So great. I hope that interests some of you in this kind of work.
It's hard to clap when you're muted. Fred, if I could lead off with a question. You said that experimentalists don't like reading out your 3 or 4 states, but some of us love it. So what would it buy you if you had, a high fidelity readout of more than 2 states? Would that be something you could fold into your process?
I think so. I mean, so, another thing that we're doing is we're working with some groups that are quantum communication groups. And so, there are some groups that think it might be interesting to communicate information at higher radix. And so that's not exactly, that's more like sort of transduction, although that means that we will have more things, more outputs of our computation that are not just qubits. I think it would definitely help us, right? Right now, we're quite limited in what we're doing, right? We're only using it for these intermediate states. There are certain operations certain computations that might work better if you had all the data grouped into a large radix single qubit, right? Or 2 qubits. And so I think, yeah, it's not something we've actually thought a lot about because most of our experimentalists don't like this, but I would love to hear more about it. And, and we definitely consider integrating measurement. I mean, it could be useful for things like qubit teleportation, for example, where we might, we need to measure the qubits. So
I was also thinking there's sort of these error aware ideas where maybe you can check to make sure it didn't fall out of the second state while you needed it to stay there or something.
Yeah.
Like that.
Yeah, there are a number of, I mean, there are a number of people who are using higher level states as sort of like guard bands or something to detect when you have an error, leakage error.
Okay, thanks. Other questions?
Yeah, I have a question. Well, first a comment. Yeah, this is really fascinating, and it seems as though like the research, especially the parts that you've described, are like designed to be cited many times by the hardware groups in the sense that like if they want to go to their program manager and show like the best performance, they have to use your algorithms, which is great. It reminds me of the Nike shoes that give you that 4% extra bounce, and you know, and then the question is, do they make it illegal, or you know, or is it? But I guess the question I had was, yeah, to what extent are experimentalists now thinking about, for example, optimizing their hardware, you know, when they're making.
Uh-oh.
I think, hang on, Jeremy's mid-comment. He'll rejoin us in a second.
You know, qubits to, let's say.
Jeremy, hang on, you have to back
hardware.
up like 2 sentences. You locked up.
Sorry. I guess what I was wondering is whether the experimentalists are now really in the loop in the sense of trying to optimize their hardware for that, minimizing the noise of their second excited state. You said that currently they're not interested in, but you know, might they be forced to do this in order to remain competitive?
I think it's possible. I think right now we're in this stage of they're trying to see how well it works with their current hardware. We had this very interesting thing with IBM where we were able to play with their third state, but it turns out they've actually tuned their wave generators to not allow you to get into the third state. So we had to duty cycle them and fool the machine into doing it. But you know, so if things look good, I'm sure they're going to change their wave generators so that we can get there more effectively and with more reliability. So I think right now, I think it's for that work, it's still in the proof of concept phase to sort of motivate vendors to, I think most machines can actually support it. It's more of an interfacing issue. So, but then they would need to optimize more for it.
Yeah, I guess the problem is the generic qubits are not really set up to be qubits. But I'm sure if we sat down and wanted to make a 3-level system that didn't favor any level, we could do that.
Right. And in fact, you know, it depends. It may be that, like, at least the way we've engineered our system, you know, it's okay to favor, you know, the first and second level because we don't use the third level very much, but maybe that would change, or, you know, maybe we'd have different kinds of devices in the machine. So, but some of the other work, for example, in pulses and with the compiler mapping, that stuff has already been adopted, right? Because it's, you know, it's much more near term. And I think that, you know, we're one of the main people who use IBM's Open Pulse interface because, you know, we do all this pulse work. I will say that the work that I showed you was sort of the simplistic view. It turns out that compiling for a large function like that doesn't work on IBM machines because the Hamiltonian isn't well characterized and the machine is too noisy. So we've actually adopted simpler pulse optimizations on their machine, which are quite effective actually. But we are waiting for more reliable machines or maybe trapped ion machines so that we can do this higher level pulse optimization.
Well, I guess I have a question there. So they're the like scarce resources, knowing what your Hamiltonian and non-Hamiltonian terms are so that you can feed them into the compiler. But that's kind of sometimes, I guess, like the here be dragons of the computer, right?
Yes. And I mean, our feeling is that, you know, for trapped ion systems, for example, I think that they're predictable enough that we could probably get a good result, but it basically doesn't work on, you know, the superconducting systems. You know, there are some small cavity-based systems that are well characterized enough that we can make it work, but they're still small, so it's not clear how that will scale.
Okay, Ginny, how are we doing on time? I guess we have to move on.
Yeah.
Okay. Last but not least, our third speaker for today is Ryan O'Donnell. He is a professor in the Department of Computer Science. He's a professor in the Department of Computer Science at CMU, where he's been since 2017. His PhD was from MIT in Applied Mathematics in 2003, and he's going to tell us today about quantum learning for quantum data. Take it away.
All right, can everybody hear me okay? See me okay? Great. Great, thanks very much for having me. It's really nice to have a Carnegie Mellon University component to all three talks. In case you didn't know, Fred's co-author in the book that he was talking about was Yongshan Din, and a CMU undergrad. I'm actually working at Microsoft this summer, so I have a bit of a dual affiliation right now. So,
thank
pardon
you
me?
for saying me Yongshan, by the way, Ryan.
Oh yeah,
He's
great
awesome.
guy. Yeah, he's a great guy. In any case, yeah, for this talk, you should really, I'm definitely much more theoretical than the other two speakers. You should basically think of me as like a mathematician for the purposes of this talk. So I'll tell you some theory of quantum learning of quantum data. Okay, so let me just say briefly what I mean by this. So the picture is you have some kind of quantum data, particles in a quantum state, and you're going to ideally use your quantum computer that is already fully operational. This is a bit fanciful and futuristic, and try to get some classical outputs. You want to characterize your quantum data using a quantum computer, but the output is, a classical description of the quantum data, ideally. And the goal here is not to do anything, faster than classical. Rather, it's to do things like not much more slowly than you would, or much less efficiently than you would do them in an analogous classical problem. So I just want to make sure that I explain what I mean here. To contrast this with the problem of quantum learning of classical data, this is another topic that people are very interested in. Here you have some, let me try using my pen here. You have some classical data, like a classical machine learning or statistics problem, and you want to use your fully functional quantum computer to solve the learning problem. So people are interested in doing this with a variety of techniques, including these linear algebra-based speedups of HHL. This is exactly what I will not be talking about. I don't have much to say about this, so cast this from your mind if this is what you're expecting. Rather, as I said, I want to stick with the problem of quantum learning of quantum data. So if you know this term, this is kind of like the tomography problem. Just a brief word on motivation if you need it. So I mean, let's say you're doing any kind of physical quantum experiment, and I don't want to get myself into trouble by talking about practice too much with so many practical people on the line. But let's say you're trying to build a quantum circuit or perform a quantum teleportation experiment or some other kind of quantum experiment where you're, in the end, trying to get some particles into a specific quantum state. Well, you better learn how well you did. You better learn what quantum state is output by your device or estimate how far it is from the desired quantum state that you're trying to produce. And you could also talk about the problem of learning quantum transformations or quantum channels. This is also very important, but let me just stick with the problem of trying to learn an unknown quantum state or estimate something about an unknown quantum state. So before I explain the problem in like a slightly more detail, let me just contrast it with the analogous classical problem, which is called classical density estimation or learning an unknown probability distribution. So this is the classical problem, which is the classical analog to the quantum problem I want to say a bit about. So in this problem, there's some unknown source of randomness, which you can think of it like as a die that comes up, the different faces with different probabilities. And we can think of this as like a probability distribution P on the D sides of the dice. So there's some unknown probabilities, P1 through PD, and you can get access to draws from this probability distribution, and you would like to, let's say, learn the probability distribution or estimate the probability distribution. So the model here is we assume it's very expensive to do an experiment. So maybe you can afford to only get some fixed number of samples, M. And OK, so if you can pay for M samples, then somebody, let's call it nature, draws M times from this probability distribution and produces some sample. Perhaps in this case, D is 3. And so you get some outcomes like 2 and 1 and 3 and 3 and 1. Maybe that's if M is 5. And your learning algorithm gets to see these samples. I only say this to contrast it with the quantum case, which we'll talk about in a moment. And then the algorithm, does some calculations or thinks for a while about the sample, and then makes some kind of estimate, which I'll call X. So now there are various tasks that you might be trying to do. I mean, the most extensive task you might try to do is just try to estimate all the probabilities P1, PD, up to some certain accuracy, call it epsilon. But maybe you might just be trying to learn something less, like maybe you want to estimate the entropy of P. Maybe you want to estimate the maximum probability of any outcome. Maybe you want to test whether P is close to like a hypothesis distribution Q you might have. So there's various things you can try to do, and let me just leave it at this. So this is a picture of, sort of the most basic problem in statistics or unsupervised learning theory, just trying to learn an unknown probability distribution. And let me now compare it to the quantum version of the problem. So here's the quantum version of the problem. It's the problem of tomography or learning an unknown mixed state. So let me emphasize here, if people know what this means, we're going to be talking about learning mixed d-dimensional states. Or if you want to think in terms of qubits, log d is the number of qubits in this state. So just cheating a tiny little bit, a quantum state, a d-level quantum state, can be thought of as, again, a probability distribution P, but instead of just being on, the outcomes 1 through D, it's a probability distribution on some D, unit vectors, orthonormal vectors. Okay, and in the quantum state learning problem, the probability distribution P1 through PD is a mystery to you. And also these unit vectors, V1 through VD, this is somehow, my fingers are like my picture of D unit vectors, are also a mystery to you. Okay, and these are the things that, this is the source of quantum randomness, the quantum state of your particles that you're trying to learn. And again, maybe you can afford to get some kind of number of samples from these quantum states. Maybe you can run your experiment m times. And we make this theoretical assumption, it's that when you do this, you get m copies of your state. Okay, and unentangled copies of your state. And the way you can think of this is you get to draw from this probability distribution on these unknown vectors, m times. But alas, as most people know about quantum, you cannot just like look at some particles and see what state they're in or see what vector the outcome was. You can only perform measurements. And I won't get into measurements, the theory of measurements at all here. But this is basically the the agency that the algorithm, the learning algorithm has. It's in how to design this measurement to try and extract information. Because the measurement does not tell you exactly what the vector outcomes are. It just gives you some probabilistic classical information about what the vectors are. So you've got like this, kind of double whammy, triple whammy situation going on here, where like the probabilities are known, the vectors are unknown, and like when you get your draw of m vectors, you can't even just directly perceive the vectors. You can only do some measurement that gives you a little bit of probabilistic information about what these vectors were. But anyway, you design your measurement and you think about your the measurement outcomes that you get, and then finally you want to estimate again something about this state. Again, you might want to estimate all the P's and all the V's. That's like estimating the whole density matrix. Or maybe you just want to estimate the P's, or maybe you just want to estimate the entropy of the P's. This is the von Neumann entropy of the state. Maybe you just want to estimate the largest P value. This will tell you something about how close to pure the state is, etc. There are many things you might try to do. Okay, and so what I've been working on for the last 5 years in this area has been about assuming everything that you would assume in theory. You have like a perfectly great quantum computer that can do any measurement you want, and the only constraints are like the laws of physics. What is the best, most efficient learning algorithm in terms of learning something about this quantum state using as few samples as you can? Okay, and the math gets very interesting, uses group theory and probability and combinatorics and lots of fun stuff. But I will skip that and just tell you some things that we've learned over the last 5 years about the complexity of this problem. So here's some results on this problem of quantum tomography. So I don't know, 4 years or so, we actually figured out in theory the most efficient algorithm for learning the entire d-dimensional state to some target accuracy epsilon in terms of trace distance or fidelity or some notion of accuracy. And the long story short is that there is a method for doing this that uses a number of copies that scales like the square of the dimension, d squared, and that this is also necessary. Like there's no algorithm that can learn a quantum state, a completely unknown quantum state in d dimensions that uses substantially fewer than square of d many copies. Another thing that was looked at, and in fact much earlier because it's a simpler problem, even dating back to work from the 80s, is the simpler task of just learning the P's, the probabilities as I called them, or these, if you know a little bit of quantum theory, these are like the eigenvalues of the unknown state. And here, we don't actually, for a positive result, we don't know anything actually much better than just learning the entire state. So we know an algorithm, a simpler algorithm that, again, needs a number of copies of the state that grows quadratically with d. But we don't know a lower bound, so it's possible to maybe do better than this. And I think it is possible to do a little bit better than this, and it's something I'm thinking about right now. There's a little bug here. Let me cross this out. This should be a d. And the last thing that I'll mention here is the task. Maybe you have a fixed quantum state, these Q's and W's that you were trying to create, and you just want to test if the state your machine does create is close to the target or far from the target. And if it's far from the target, you don't want to learn what it is. You just want to know, like, oh, this is quite wrong. So for this task, we showed that you can do better than this quadratic scaling. There's like a hypothesis tester or a state certification algorithm that uses only a linear in the dimension number of copies of the state, and that linear is necessary. Now, as I'll mention later, this is all great, like in theory, and but it's actually kind of sad in theory if you think about the fact that this dimension d is exponential in the number of qubits. So if you just write it as d, things scaling like d or d squared seem good. But if you remember this is exponential in number of qubits, that's not so good. So there's some results I can also mention that are better along these lines. And these generally have to do with the case where the state you're trying to learn is either of low rank, meaning it's kind of close to pure, or is close to having low rank. And in general, some of these Ds can turn into the K, the rank of the state, which is like the number of non-zero Ps, or maybe the number of, you should think of them as the number of large P values. OK, so for this, if you want to learn an entire state that has rank K, where there's at most K non-zero PIs, then you can do this with a number of copies that scales like K times D. So it still has the D dependence, but rather than being quadratic in D, it's like K times D. On the other hand, if you just don't want to learn the whole state, but you want to only estimate, let's say, the largest few eigenvalues of the state that give you some sense of how close to pure it is, this you can finally do with a number of copies or samples that doesn't depend on the ambient dimension D. It's quadratic in the rank. And finally, again, you can do even better if you're not trying to just, let's say, learn the whole state, but only confirm the state or disconfirm that the state is close to some particular state that you were trying to create. And there you can do it with a number of samples that's linear in the rank. OK, so these are some mathematical results that we've developed over the last 5 years, and I'm still thinking about some various aspects of this. But let me say some words about the practical efficiency of these problems, and it will remain like the practical to a theorist versions of this question. So first of all, I mean, this task of quantum tomography, or like quantum learning of quantum data, is done experimentally all the time. So people are definitely interested in trying to do this practically, and also trying to learn, quantum channels, or trying to characterize quantum noise models. These are things that people all want to do today. But these are some motivations I threw up there. But nobody ever uses any of these algorithms that I've discovered, which are the optimal algorithms. So why not? There's very many reasons, but I'll tell you 2 reasons. One is they use entangled measurements. So if you are trying to learn the state of 5 qubits, and you get like a bunch of copies of these 5 qubits, maybe you have like now 100 qubits or 1,000 qubits, then the measurements that are optimal for learning this state, are like entangled measurements that like touch all the qubits at the same time. So this is not very practical, and the task of implementing these measurements is as hard as building a full-scale quantum computer. So this is obviously something we're not able to do these days. So here's how a theorist would model like a simpler version of the problem. You could ask for algorithms that don't measure the copy, don't collect up like many copies of the state and do one giant entangled measurement. You might ask for like a learning algorithm that just takes one copy of the state, measures it, gets some information, that gets another copy of the state, measures it in some way, and gets some information, and so forth. You could even imagine allowing sort of like an adaptive algorithm where you do different measurements based on what you've measured before. But this is like a restricted class of algorithms, and you could ask for what are the optimal algorithms in theory for this scenario. Here, some things are known. For example, if you want to learn the entire state, then it's known that it's sort of necessary and sufficient in this weaker model to use a number of copies that scales like the cube of the dimension. So that's better than like the most naive thing that you could talk about, but it's still quite expensive. And so there's been recent work about trying to solve simpler problems, but in this model where you can only do these one sample measurements.
Ryan, it seems like you're wrapping up, but give you a
Yeah.
time here.
I'll just talk for one more minute.
Okay.
Thanks. Finally, this other issue that I mentioned is that all these algorithms that have a dependence on d, the dimension, this is really d is exponential in the number of qubits you have. So any algorithm that really has a scaling on d that's not like log d or no scaling on d is kind of useless in practice. So this is trouble if you just take the standard version of the problem of trying to learn an unknown quantum state. So it means you need to change the problem. So there's various ways you can change the problem. One is this a very interesting way called shadow tomography proposed by Scott Aronson in 2016. And this allows you to do efficient things that are efficient even in terms of the number of qubits. I don't have more time to talk about these things. So let me just say that I have some new results in this area that are forthcoming that I hope to tell you about another time. So that's all I have to say. Thanks.
So this is interesting. When we work in the lab, we tell the students, you can do tomography on 2 qubits. You can kind of do tomography on 3 qubits, and then past that you should give up. And I feel like this is in a much more sophisticated language, something of a similar statement, right? That we're just never going to do tomography on a 1,000 qubit machine. Or full tomography.
Full tomography, yeah, because first of all, you cannot even write down the answer. I mean, just writing down the answer, the state of the system, needs d squared numbers, which is 4 to the power of the number of qubits. So yeah, you're probably not going to literally do full tomography if there's more than, I don't know, 10 qubits or something, which is okay. Maybe you'd want to do that. Of course, these are maybe algorithms from 25 years in the future. If you want to use full tomography, you might use these algorithms once you have your fully operational, 100% accurate quantum computer. Yeah, I mean, practically speaking, another angle you might go on right now is even, what kind of tomography can you do if, there's state preparation and measurement errors and your gates are imperfect that you're trying to implement the algorithm with and so forth. So I'm thinking a little bit about this too, but you're definitely right that in practice, 2 or 3 or 4 qubits, I mean, is what you might be able to handle.
Okay. Other questions?
So it seems like the practical application of this would be that you would do some sort of property testing or look on the distribution, right? So you wouldn't actually have to measure all of the quantities.
Right.
And I guess like things like the top K or things like that might be interesting things you would do. So not only would you only need to learn that, but you would only need to, or maybe you could even measure even as well. I guess you would only need to learn as much as you need to measure, or you want to measure.
Yeah, ideally. So I mean, if you want to, let's say, estimate the top few eigenvalues, you can do this with a number of copies that doesn't involve the scale with the number of qubits, which is good. But if you want to also learn the associated eigenvectors, well, I mean, if you have to write down d numbers, it's going to take you d time. So you can't, in some sense, that's sort of why these kinds of things are as best possible.
Yeah.
But, there's different ways to try to get around this thing. For example, the shadow tomography is, well, if you can learn the expectation value of exponentially many observables sort of quite efficiently. And maybe that's good enough for you. Maybe you don't want to learn the whole state. You just want to learn the expectation value of some observables.
Interesting. You had a site there that was like 1957 or?
Yeah, 1967. I saw some paper say that this person, Janes, sort of had the same idea of quantum shadow tomography as Aronson back in 1957. I looked at the paper. I couldn't quite tease it out, but I couldn't also exactly refute that. So I threw it in there just to be, polite to James.
I thought you were saying it's going to come out in 2057. Now that would have been really interesting part of the talk.
This apostrophe is very ambiguous, like this.
I wanted to bring up something in Fred's talk. I was actually very encouraged with this idea of compiling. Didn't have time, obviously, to talk today, but wrote a couple papers trying to compile, on the NIST circuit. Obviously, to incorporate noise is quite complicated. But I think the idea that you guys are going is better. This multi-step process of taking an idealized circuit, putting it on a physical circuit that is noisy, and then saying, "Oh my God, what shall I do with it?" I think you're skipping. You're kind of optimizing that two steps. That is actually very that I think is very encouraging. I was wondering if there's a way some of my postdocs or PhD students could find out what's going on and contribute there, since we started down that path of this step-by-step compiling, and we thought, hey, that's not a good use. But your framework actually is more encouraging with respect to grabbing it all and then saying, look, get the aggregate thing about right and kind of move on. So I just wanted to bring that up as something that was very interesting.
Yeah, I think it's a very powerful approach, and in fact, that the book we just wrote is probably a good place to start. Those books are actually designed to help researchers get started in different areas, and they're written in many different disciplines. I will say that it's not without cost, right? There's a reason why we have layers in software, because once you break the layers, then the complexity grows, quite quickly. We can get away with it because we have small machines and small programs, and we're trying to be really strategic about which things we sort of unify in the stack.
So one path I didn't hear you say, maybe you're doing it, is restrict classes of problems and compile only for those problems for this hardware. So, I mean, I'm going back to the old way of thinking that the hardware is really problem-specific optimized, rather than it be general-purpose optimized. Any thoughts on that?
Well, right now, the hardware tends to look fairly uniform, right? You can sort of think of it as a sea of bits that you can do any operation on, but it is going to differentiate itself. We did some work in the past. If we start doing different kinds of error correction, we might specialize at some level. If we start using mixed technologies, there are some technologies might be better at storing qubits, and some might be better at manipulating qubits. The big sort of technical hurdle there is transduction between technologies. But if we could convert between technologies, then you would have a situation much like classical machines, where we have differentiation because the technology is better for certain things, right? But right now the machines are a little bit homogeneous, so you don't really see that so much. Certainly the software tool chain would tailor itself to the application, and that is what we do. In the classical world, we call this sort of domain-specific languages and domain-specific software stacks. And so quantum computation is sort of the extreme version of that, really, because it's a very narrow space. And also typically we're willing to compile for a specific problem, specific input, right? So it's as specialized as it can be.
Okay, well, we've kind of opened it up already to questions for all three speakers. Are there any more from the YouTube or from the audience?
Sorry, Michael,
go ahead.
Go. No, you.
I'm calling for questions. You look like you have one. Please be a customer.
Oh no, I was going to say it sounded like a good time to maybe to wrap things up.
Okay.
I mean, it could have just been a freeze and rather than a pause.
Okay. Well, okay then. In that case, thanks everybody for coming. Our three speakers for speaking. Our as usual, invisible internet audience and our visible internet audience. And we'll see you all next time.
Thank you.
Thanks.
Yeah, I just want to point out that before we leave, Scott Harrison is our public lecturer this year, and his talk is tentatively scheduled at August 20th. So everyone today is invited, especially Ryan, if you want to hear more about his shadow tomography. Did I get the word right? So yeah, stay tuned.